Today we are going to present about our project-based learning. I'll introduce our group members first. We have Fakri, Shami, my name is Shame, Nakiuddin, and Sofian. So moving on to the introduction. So our project-based learning study basically examines the mechanical properties and internal structure of medium carbon steel, evaluates overall quality and performance. We carry out tensile testing, hardness measurement, and metallographic analysis to investigate how the material's internal features influence its strength, ductility, and overall behavior. By correlating these results with microstructural observations, we gain a comprehensive understanding of the steel's performance. This hands-on study also provides us with valuable experience in problem solving, teamwork, and critical thinking, linking our theoretical concepts to practical and real-world material assessment. And I'll pass it to my group mate Sophia next.
For the research, planning, and experimental design, we do at week 2 briefing, at week 3 metallography sample preparation, at week 4 grading and polishing. Yes, at week 5 also grading and polishing. At week 6 we do etching. Week 7 we don't do anything because I think it's holiday. Week 8 we do stencil testing. At week 9 we do hardness testing, and for the week 10 we do a final report.
So here is the part where we including all the materials testing techniques. So here we have three parts of the techniques, which is the first one is we have the metallography, second one we have the tensile test, and the last one we have the hardness test. For metallography, we have 5 processes, which is the first one is the sectioning, second one is mounting, the third one is grinding, fourth one is polishing, and lastly we will do the etching. So for the tensile test, we will use the dog bone shaped specimen, and then we also use the 100 kilonewton universal testing machine. Next, we will use the speed, which is the cross head speed of 10 millimeter per minute. And lastly, the load will be applied to the specimen until the specimen will be break. Next, for the hardness test, we will use Rockwell hardness method, which is HRC. We will use the diamond cone indenter to make a point at the specimen, and then we will apply 100 Newton load at the specimen. Lastly, the experiment will be repeated on the several points of the specimen to have more specific readings.
Analysis and interpretation. From our given data, we have been given 4 types of magnification: 5 times magnification, 10 times magnification, 50 times, and also 100 times magnification. From the picture given, we did our research, and the 10 times and 50 times magnification shows that the materials shapes like the grape botryoidal, which is the grape like material. And for the 100 times magnification, we can see that there is a marked cracks shape on the material. From these findings, we did our test, which is the hardness test and also tensile test. The target specification for hardness test is between 50 to 60 HRC, which is the Rockwell, and also approximately 550 and 700 hardness. From our experiments in the lab using the carbon steel, it yields significantly lower average hardness, which is 21.57 HRC and 246.23 HV hardness because. And also, the tensile test analysis shows that it is typically a bit low from the target specification, which is 1,500 megapascal. But the samples we used only give us 588 megapascals and also 490 megapascal. From this analysis, there are several possible complaints from the company, which is first one is the premature wear and deformation. The complaint is that the plates wear out rapidly or deform under heavy loads, which cause the decarburization, which is the soft ferritic layer, lowers hardness, the tensile strength, and reducing wear resistance. The second one is surface instability, which is flaking. The company might also say that the poor surface finish and loose material jamming the machinery, which cause the oxide clusters. It shows that the grape-like scale is brittle and loosely adherent. It detaches easily during operation. And the third one is unexpected brittle fracture, which is sudden and catastrophic cracking during installation. It caused by the surface glazing, which can be seen by the dry mud cracks as the stress concentration. This causes rapid failure under tensile load. This one can be seen under the 100 times magnifications from the material given just now.
So move on to the root cause analysis. The root cause for the material is severe high temperature oxidation and surface decarburization. So this failure mechanism occur in the following sequence. First, is lack of atmosphere control. This is the primary cause. The furnace operated without an inert gas atmosphere like the nitrogen. So oxygen react aggressively with the iron at temperature above 850 degrees Celsius, which cause the oxidation. Then second one is accelerated oxidation. The furnace temperature was too high, nearing the steel's melting point. This caused incipient melting at grain boundaries and destroy the surface cohesions. Next is the carbon depletion or decarburization. So the oxygen is consumed at the surface of carbon. The surface transformed into soft ferrite instead of hard martensite. This caused the significant drop in hardness. And lastly is the thermal shock, and also can be called as mud cracks. So the brittle oxide shell and the steel core contract at the different rate, which rapid cooling, which when rapid cooling or quenching, we shatter the oxide layer and creating the network of crack. So moving on, the proposed solution for this, we have three proposed solution to make this material become more stronger. First, optimize heat treatment to prevent the oxidation. So the action that we need to take is to switch to a controlled atmosphere furnace. So the method is to introduce the inert gas like nitrogen or argon to create an oxygen-free environment in the furnace. So the result from this solution, the material will stop brittle, scale formation and carbon depletion to ensuring high strength which by the martensites. Second one is to improve the quality control, the incoming inspection. So the action that be taken is to implement the metallography analysis for the every batch. So the method is to cut and polish a sample to physically measure outside scale depth and check for the decarburization. So the result from this method is to prevent the defective material from reaching the client. Lastly, this proposed solution is to use alternative material. The specific alloy need to be selected based on the client's need to avoid cracking. So first, for high toughness, we can switch to IC 4140 or chromium molybdenum. It use an oil quench, which is lower than water to reducing the thermal shock. And second one is for surface durability, we can switch to ICD2 or 2 steel. This material is use a hardening or slow cooling, which will eliminate cracking risk.
Okay, now to conclude our our PBL. In this study, the steel sample was evaluated using metallography, tensile testing, and hardness measurements. The results indicate that the steel did not reach the expected properties of a properly hardened medium carbon steel. Microscopic analysis showed severe surface oxidation, decarburization, and the lack of martens, martens, martensitic structure, while mechanical tests revealed lower than expected strength hardness. So the suggested improvements that we have provided include using controlled atmosphere furnaces, stricter incoming material checks, and exploring alternative alloys and materials. Overall, the study emphasizes the value of combining mechanical and microstructural testing to identify quality issues and ensure reliable steel performance. And thank you.